Okay, so we reach this point where we obtain a bound for phi of u in this norm of the norm we define for the set E of TA. Okay, and so we can fix A equal to 2C norm of u not 2. Okay, obtaining and we can take T positive such that, okay, so if we include this here, 2 alpha, C alpha, mu naught 2 alpha minus 1 lambda T theta. Okay, so what we want is to take T positive such that we can make this less than 1. So in a way we can bound this, obtaining a u naught norm 2 factor, common factor, and in a way we can say that phi is well defined in ETA. Okay, in ETA. Okay, now if u, b are in ETA, we will have that phi b minus phi u. Okay, t we want to be equal to I lambda 0 t e I t minus t prime population absolute value of p alpha minus 1 multiplied by b minus absolute value of u minus alpha minus 1 u all of this t prime dt. Okay, here's a dt prime. Okay, so now we will use the same argument that we used before to bound now the difference between phi of b and phi of u. Okay, 0t, that will be between norms phi b, phi u, t r alpha plus 1 dt 1 over r, and now the same thing that we did before, we will bound this by c absolute value of lambda 0 t absolute value of p alpha minus 1 b minus u alpha minus 1 u all of this norm r prime alpha plus 1 over alpha dt 1 over r prime. So this is less than equal than c alpha lambda integral c 0 t norm of p, okay, parenthesis, alpha minus 1 alpha plus 1 plus u, again alpha minus 1 alpha plus 1 r prime. Now if we separate all this in a good way, we can obtain on this side this, and then here multiply the norm of b minus u r prime alpha plus 1 plus 1, okay, well, t dt 1 r prime. Okay, and this will be less than equal than c of alpha lambda now appears again d theta. Now we will have integral 0 t of b r alpha plus 1 dt, and now we change the exponent. It's going to be alpha minus 1 r plus, well, now we'll have the same, but for u alpha plus 1 dt alpha minus 1 r. Okay, and multiply this by a factor. I'm going to write it down here. Now it has to appear this is the integral between 0 and t of bt minus ut r alpha plus 1 dt, and now we already changed the exponents, so now we have 1 over r. Okay, so we have the bound using similar ways of the difference of phi b and phi. Once again, we can also bound the supremum of the differences of the phi's of u and b, but now in norm 2 with the supremum between 0 and t. This can be bound well, c alpha 2 by c multiplied by c on alpha lambda t theta a alpha minus 1, and finally integral between 0 and t of b of t minus u of t or alpha plus 1 dt 1 over r. Okay, so once again we have the bound for this part and the bound for the part of the supremum of the norm 2. So once again, if we choose a less than equal to c u naught 2, okay, and using the inequality that we had before, we have the 2c lambda t theta a alpha minus 1 less than equal to alpha c alpha lambda t theta u naught alpha minus 1 2, and this will be all because of the inequality that we had in the last video, less than 1. So then we will have that for t, the t will be almost equal to u naught beta, and let's say this exponent would come from here. Beta will be 4 1 minus alpha over 4 minus n alpha minus 1. Okay, so we have the existence and uniqueness in, let's say, an appropriate class of the solution of the equation. Okay, so we already established which is the class of the set where we're going to have the solution. Okay, so now let's see the continuous dependence. Okay, so if we have u and v solutions of the the equation in the form of the Helmholtz principle, then we have that ut minus ub bt will be equal to EIT relation the two initial conditions r lambda multiplied by what is right here plus I lambda the integral 0 t of EIT minus t prime operation u to the alpha minus 1 u minus b alpha minus 1 b t prime dt prime. Okay, so using the same arguments we have been using, we have the integral of 0 t of ut minus bt r alpha plus 1 dt1 over r. This will be less than equal than c u naught b naught 2 plus, not the bound for this, let's say we have a k alpha lambda t theta u naught 2 alpha minus 1 plus b naught alpha minus 1 2, this multiplied by integral 0 t of ut minus bt r alpha plus 1 tt1 over r. Okay, so if we can take u naught minus b naught small enough, we can bound, as we've been doing, we can bound this integral, that is the part that we have to bound, because the other stuff is all independence of u naught b naught. Okay, so we can bound, if we take u naught minus b naught, the norm to small enough, the following way: 0 t ut minus bt r alpha plus 1 dt 1 over r less than equal than, let's say, a k line u naught minus b naught 2. Okay, and in the same way we can prove for the other part that we have to bound, that the supremum 0 t ut minus bt 2 is less than equal than, again, k little line u naught minus b naught norm 2. In this way um, we will have both bounds. Okay, so we will be in this part, then this part, and we have the whole bound, and then we will have continuity for continuous dependence, which completes the proof with this continuous dependence for phi. Okay.